Welcome back to AI.Code.Cast. Sometimes the simplest problems, you wouldn't think it'd be that hard, can really pack an algorithmic punch.
Oh, yeah, definitely.
Today we're diving into one of those figuring out the minimum number of steps to turn one string into an anagram of another.
Kind of like a word puzzle, but with a coding twist.
Exactly. And before we get into the nitty-gritty, let's make sure we're all on the same page. For those who might be new to the concept, an anagram is just rearranging the letters of a word to make a new one,
Right.
like silent and listen.
Yeah. So the challenge here isn't just recognizing if two words are anagrams.
Right.
It's figuring out the most efficient way to transform one into the other. We're talking minimum steps, folks.
Minimum steps, yeah. And that's where things get interesting.
Yeah.
If we were just randomly swapping letters around, we could be here all day, especially with long words.
Right. That's the brute force approach. Just try every single combination until you stumble upon the anagram. Incredibly inefficient, especially as the word length increases.
Yeah, brute force is out. So what's a smarter way to tackle this? Our sources point to something called frequency arrays as a key technique.
Frequency arrays are super useful for these kinds of problems. Instead of comparing letters one by one, we're going to count how many times each letter appears in each word.
So instead of getting lost in the individual letters, we're looking at the overall composition of each word.
Exactly. It's like taking inventory of our building blocks. So if we have the word listen, we'd count one L, one I, one S, one T, one E, and one N.
And we do the same for the target word, silent, in this case.
Mm-hmm.
So how does just counting letters help us figure out the minimum steps to transform one word into the other?
Okay, so think of it this way. Once we have those counts, we can directly compare them. Any differences in those counts tell us which letters we need to change and how many changes we need to make.
So we're essentially pinpointing the discrepancies between the two words.
Exactly. And by adding up all those differences, we get the minimum number of steps needed to turn one word into an anagram of the other.
Okay, I think I'm starting to see the light here. But before we dive into specific solutions, what are some common pitfalls people might run into when approaching this problem?
I think one common mistake is forgetting to handle cases where the input strings are of different length. Remember, for a valid anagram, the strings must be of the same length.
That's a good point. If the lengths don't match, right away, they can't be anagrams.
Right. Another thing to watch out for is case sensitivity. If the problem doesn't specify whether capitalization matters, you'll need to decide how to handle it. You could convert everything to lowercase or uppercase before processing, or treat uppercase and lowercase as distinct characters.
So always double check those details before jumping into the code. Any other tips or tricks you'd like to share?
Don't be afraid to test your code thoroughly with different input strings, including edge cases like empty strings, or strings with only one character. It's the best way to make sure your solution is robust and handles everything correctly.
Great advice. Okay, so we've got the problem defined, we've talked about the pitfalls to avoid, and we have a general idea of how frequency arrays can help. I'm itching to see how this all comes together in an actual solution.
Me too. Let's take a look at one of the solutions in our source material that utilizes a hash map to solve this problem.
Ooh, hash maps. Those are always fun. Maybe a little refresher on how those work before we jump in.
Sure. Think of a hash map like a dictionary. You have keys, the words you look up, and each key is paired with a value, the definition. In this case, our keys would be the letters of the alphabet, and the values would be the counts of how many times each letter appears.
So listen, the key would have a value of 1. I would also have a value of 1, and so on.
You got it. And we do the same for silent, storing its letter counts in the same hash map.
Okay, so we're building this hash map, but how does that lead us to the minimum number of steps? This is the part where I usually get lost.
Okay, here's where it gets clever. As we count the letters in the second word, we can actually decrement the count for each letter that's already in the hash map from the first word.
Hold on, decrement. So if we see an L in silent, and L already has a count of 1 from listen, we decrease the count back to 0.
Exactly. We're essentially canceling out the letters that are already in the right place. Anything with a count of 0 at the end means those letters match up perfectly between the two words.
That's brilliant. So we only need to worry about the letters that don't cancel out.
Precisely. Any letter with a positive count at the end means it appears more times in the first word than the second. And the sum of all those positive counts tells us how many letters need to be changed.
Okay, I'm really starting to see the power of this approach. But wouldn't using a hash map be less efficient than a plain array, especially in terms of memory?
It depends. Hash maps can be more memory intensive, especially if we were dealing with a huge set of characters. But for lowercase English letters, it's not a big deal. And the time savings we get from using a hash map often outweigh the memory cost.
That makes sense. Speed versus memory, it's the eternal struggle. But I'm noticing that another solution uses a plain array instead of a hash map. Is there a reason for that?
Good eye. That solution takes advantage of the fact that we're dealing with only 26 lowercase English letters. So instead of a hash map, it uses an array with 26 slots each representing a letter of the alphabet.
Ah, so it's like a streamlined version of the hash map, custom built for this specific scenario.
You got it. And it's even more memory efficient since we're only using space for those 26 letters.
This is great. I'm loving how these solutions are building on each other. We've gone from brute force to frequency arrays, and now we're seeing different ways to implement them using hash maps and arrays.
And guess what? There's an even more optimized solution that combines the best of both worlds. It's the single pass solution we mentioned earlier, the one that's like speed reading for algorithm.
Oh yeah, that one. I'm all ears. Tell me how the speed reading magic works.
Okay, so remember our building block analogy.
Uh-huh.
This solution takes that to a whole new level. So instead of building separate structures and then comparing them, we're going to analyze both words simultaneously, like we're walking along two rows of those blocks at the same time.
Okay, I'm visualizing it. I got my 2 rows of blocks, one for listen and one for silent. What do I do next?
So you have 2 pointers, one for each word, starting at the beginning. As you move along the rows, you'll have a helper keeping track of the differences between the blocks.
So if my listen pointer is on L and my silent pointer is also on L, the helper notes that we're good.
Exactly. But if your listen pointer is on L and your silent pointer is on T, the helper notes our short ones is and have an extra T.
Okay, so it's like we're constantly adjusting our inventory as we move along the rows.
I like it. And at the end of your walk, your helper's notes will tell you exactly how many blocks you need to swap to make the 2 rows identical.
That's such a cool way to visualize it. So this single pass method is basically doing the same thing as the frequency arrays, but in a much more streamlined way.
Precisely. And because we're only making one pass through the words, it's incredibly efficient, especially for long words.
Okay, this is all starting to click now. But how does this translate into code? I'm guessing it's not literally pointers and helpers running around.
Right, it's a bit more abstract than that. Instead of pointers, we use index variables to keep track of our position in each word.
Okay.
And instead of a human helper, we use, you guessed it, an array.
I should have seen that coming.
Yeah.
So the array is our helper's notepad, keeping track of the differences.
Exactly. Each slot in the array represents a letter of the alphabet, and the value in that slot represents the difference in count between the 2 words for that letter.
So as we move through the words, we increment the count for the letter in the first word and decrement the count for the letter in the second word, all within the same loop.
You're getting it. It's all about simultaneous processing. And just like in the previous solutions, once we've gone through both words, we simply add up the positive values in our array to get the minimum number of steps.
I am seriously impressed with how elegant this solution is. It's fast, it's memory efficient, and it's conceptually clear.
That's the beauty of a well-designed algorithm. But you know me, I always have to ask, is there anything we could do to optimize this even further?
That's a good question. We're already doing a single pass, and our space complexity is 0.1 because we're using a fixed size array. What else could we tweak?
Well, there are always micro-optimizations you could explore, like minimizing the number of array accesses or using bitwise operations for counting. But I think the real gains come from understanding the trade-offs between different approaches and choosing the one that best suits your specific needs.
That's a great point. It's not always about squeezing out every last drop of performance.
Yeah.
Sometimes the most elegant solution is the one that strikes the right balance between speed memory usage and readability.
Absolutely. And speaking of readability, we've talked a lot about the conceptual side of these solutions, but I think it would be helpful to look at some pseudocode to see how these ideas translate into an actual algorithm.
You read my mind. Let's start with a hash map solution. How would we represent that in pseudocode?
All right, imagine we have a function called min_steps_anagram that takes 2 strings, word 1 and word 2, as input.
Got it. So min_steps_anagram, listen, silent, would give us the minimum number of steps to transform listen into silent.
Exactly. Inside this function, we first create an empty hash map called letter counts.
Okay, so that's our dictionary ready to store our letter frequencies. What's next?
We loop through each character in word 1. For each character, we check if it already exists as a key in our hash map.
If it does, we increment the count. If it doesn't, we add it to the hash map with a count of 1.
You got it. So after this loop, our hash map contains the frequency of each letter in word 1.
Then we do a similar loop for word 2, right?
Yes, but with a twist. This time, instead of incrementing the count, we decrement it. Remember, we're canceling out matching letters.
Right. So if a letter from word 2 already exists in the hash map, we decrease its count. If it doesn't exist, we add it with a count of making 1.
Precisely. Now, the fun part. We initialize a variable called steps to 0. This will store our minimum steps.
And I'm guessing we loop through our hash map now, adding up all the positive counts?
You're on fire! We iterate through each key value pair in the hash map. For each value that's greater than 0, we add it to steps.
And finally, we return steps, which represents the minimum number of steps needed to transform word 1 into an anagram of word 2 using the hash map approach.
Nailed it. That's the essence of the hash map solution in pseudocode. It's all about leveraging the power of a hash map to efficiently store and manipulate letter frequencies.
This is fantastic. I'm feeling a lot more confident about tackling this kind of problem now. But what of the array-based solution? How does that differ in pseudocode?
The array-based solution is very similar in logic, but instead of a hash map, we'll use an array of size 26 to represent the lowercase English alphabet.
Okay, so each index in the array will correspond to a letter like A at index 0, B at index 1, and so on.
Exactly. So let's call this array letter counts. We'll initialize all its elements to 0.
Makes sense. Then we loop through word 1, just like we did with the hash map solution, right?
Right. But instead of checking if a key exists in a hash map, we directly access the corresponding array index for each character. So if we encounter A in word 1, we increment the value at letter counts.
And for word 2, we decrement the corresponding array value for each character.
You got it. Now, after processing both words, our letter counts array holds the differences in letter frequencies between the two words.
Then we just loop through the array, adding up all the positive values to get our steps count, just like before.
Precisely. And finally, we return steps as the minimum number of steps needed for the array-based approach.
So both the hash map and array-based solutions achieve the same goal, but they use different data structures to represent the letter frequencies.
That's right. The hash map is more general purpose and can handle a wider range of characters, while the array is more specialized and optimized for the specific problem involving lowercase English letters.
I'm really appreciating how these different solutions highlight the trade-offs between flexibility and efficiency. But before we wrap up, I can't resist asking about the single-pass solution one more time. Can we see how that magical algorithm translates into pseudocode?
Of course. The single-pass solution is where things get really sleek. We'll still use an array of size 26, just like in the array-based solution. Let's call it letter counts again, and initialize all elements to 0.
Okay, so far so good. Starting to feel familiar.
Now, instead of having separate loops for word 1 and word 2, we'll have a single loop that processes both words concurrently.
So we'll need 2 index variables, one for each word to keep track of our position. Let's call them index 1 and index 2, both initialized to 0.
Perfect. Now, inside our loop, we increment the value at letter counts at index 1 corresponding to the character at word 1 index 1.
And at the same time, we decrement the value at letter counts index 2, corresponding to the character at word 2 index 2.
Exactly. Then we increment both index 1 and index 2 to move to the next characters in each word.
And we keep doing this until we reach the end of either word.
Right. After the loop, our letter counts array will hold the differences in letter frequencies, just like in the previous solutions.
And then we simply loop through the array, sum up the positive values, and return the result as the minimum number of steps.
You nailed it. The single-pass solution is all about simultaneous processing and leveraging the efficiency of a fixed-size array.
Wow. I'm absolutely blown away by the ingenuity of this approach. It's a beautiful example of how a clever algorithm can significantly optimize a problem.
It really is, and it highlights the importance of thinking outside the box and exploring different ways to approach a problem.
I think we've thoroughly dissected this anagram problem from every angle. We've covered brute force, frequency arrays, hash maps, arrays, and even a single-pass algorithm.
And we've seen how pseudocode can help us bridge the gap between those abstract concepts and concrete implementations.
This has been an amazing deep dive. We hope you learned something new about anagrams, algorithms, and the art of problem solving. Until next time, keep coding, keep learning, and keep those algorithms humming.